Today's the first tutorial. In the last class, I emphasised this idea of plane waves as building blocks, plane waves as bricks, plane waves as objects out of which we can synthesise an arbitrary wave function. The mathematics of adding up plane waves to synthesise arbitrary functions, or the opposite process, taking arbitrary functions and decomposing them into sums of plane waves. So this idea of decomposition, breaking up functions into sums of plane waves, or synthesis, are two sides of a coin. And I can just wave my hands around and vaguely say, let's add up plane waves to make arbitrary functions. But at the end of the day, we need to be precise, to be mathematically precise, and to work out how to mathematise these statements regarding decomposition and synthesis. So what we're going to go through today, in working through exercise 9 in full detail, is what you need to know about Fourier analysis, the mathematics of adding plane waves to synthesise functions, or the opposite process of decomposition. Everything you need to know regarding Fourier analysis in the context of quantum mechanics is going to be covered now. This is an envelope. This is a genuine back of the envelope calculation. All right. So the first concept I want to begin with is this idea of a Dirac delta. Now, in many books, you'll see this referred to as the Dirac delta function. I don't like the use of the term function because the Dirac delta is too bizarre, too singular, too badly behaved to be worthy of the name function. This is a much more radical beast, which is actually not a function in the typical sense of the term, because it's too bizarre, it's too singular, it's too crazy. So I'll speak of this thing as a Dirac delta. So what is it? Let me give you a function which is not the Dirac delta. What I'm going to do is to plot some function which is 0, and then it's 1, and then it's 0 again. So this is a top hat function. It either has a value of 0 or 1, and this thing has a width of w and a height of 1 on w. Yep. So this function, which I'm going to call delta, it's a function of position x. This is a capital delta, not the Dirac delta. This is a capital delta. It's going to be a function of position x, but it's also a function of the width w. So this is a function, right? It's just a top hat function. It takes a value of 1 or 0, depending on whether the magnitude of x is less than or equal to, sorry, this thing equals 1 if the magnitude of x is less than w on 2 and 0 otherwise. Now this is not this is a function. How do we take this object and turn it into a Dirac delta? How do we turn this function and turn it into something which is not a function? This is the Dirac delta. What we're going to do is to take an extreme. I'm going to take the limit as w tends to 0 from above. Yeah, so w is going to be positive, the width must be positive, but I'm going to make that number w infinitely small. So this is going to become an infinitely skinny, infinitely high blip. And that's the key point. The Dirac delta is defined as a limit of this sequence of functions, and this Dirac delta is an infinitely high, infinitely narrow blip. But from the way it's been set up, the area of this object is 1. Yeah? The area under this curve, even when it's infinitely skinny and infinitely high, it has a width of w and height of 1 on w. Sure, w is infinitely small, but the area is 1 on w times w, which is 1. So the area under this graph is 1. Now I'm writing down a one-dimensional form of the Dirac delta. We'll get a three-dimensional form in due course. That, by the way, is, we'll get a three-dimensional form in due course. Here is one way of defining a Dirac delta. Any way which leads to an infinitely skinny, infinitely high curve, which has an area of 1, is a valid way of defining the Dirac delta. This definition is not unique. So this is our Dirac delta. I've just made the point that its area is 1, and again this is a one-dimensional form of 18. So I invite you to compare this with equation 18, which just writes this in the three-dimensional form. There's a second equation we now want to do. Again, I'm giving you the full toolkit of Fourier analysis, the full toolkit. That's not a tongue twister. All right. The next property that I want to give is the following. Suppose I give you any function f of x, or more precisely, any well-behaved function. I want this function to be continuous and differentiable. Any well-behaved function f. I can draw it without taking my chalk off the board. And now I'm going to stick a Dirac delta there. Now delta of x would be an infinitely skinny, infinitely high blip at the origin. But I'm going to shift this to the position x0. And then I'm going to integrate. And the question is what happens? What's going to happen, and I'm going to demonstrate this now, is that you pick out or sift. This is called the sifting property of the Dirac delta. You pick out or you sift the value of the function f of x at the point x0. And I want to motivate this pictorially. This is not a proof. So here we have our function f of x. And it's continuous and differentiable and single valued, so I could draw it with a smooth curve without taking my chalk off the board. This is f of x. I now multiply by a Dirac delta, which is going to be located at x0. This infinitely skinny, infinitely high blip with area 1. All right, here's f of x. Here's our Dirac delta. Here's the integral we want to determine. So I'm going to do something now. We've got the product of f of x with the Dirac delta, product of f of x with the Dirac delta, and my question to you is, how can I justify doing the following? How can I justify saying this is approximately equal to, I'm just writing the function out again, or the integral out again. How can I justify putting a naught subscript here? Yep. How can I justify replacing f of x? Here's a function f of x in its full glory. How can I replace this with f of x naught? Over to you. Yep. Beautiful. The delta function is 0 everywhere except for x naught. So this product, if I replace f of x with the value that it takes, this is the value f at x0. I'm replacing this function f of x with a constant f of x0. But as was stated, because the Dirac delta is 0 everywhere except at x0, the product of the yellow curve with the blue curve is correct at the point x equals x0. Away from the point x equals x0, well, this is 0. Okay, I'll bugger this up because f of x is certainly not equal to f of x0 away from x0, but you're multiplying by 0, so it makes no difference. So this, like I've written this as an approximation, but if the Dirac delta is infinitely skinny and f of x is well behaved in the sense described earlier, then this is actually an equality. F of x is now a constant, or f of x0 is now a constant, so we can pull it outside the front of the integral. What integral is left? It's the following object. Remember, by the way, there's only 3 tools in Fourier analysis, and we're working through them now. There's only 3 tools, we're working through them now. How do I continue? A flippant answer is you've got 3 tools, you need to use one of them. If you know which one to use it. If you don't, just try one and see if it works, right? We've only got 2 tools so far. In fact, we've only got 1 tool so far, right? We're developing the second. The first tool is the fact that the Dirac delta has area of 1. The second tool is what we're developing, the sifting property of the Dirac delta. We've only have really 1 tool to use, which is that the area under the Dirac delta is 1. The fact that it's transversely shifted is irrelevant. This area is 1. And so we get that this yellow equation equals f of x naught, which is precisely the sifting property of the Dirac delta. And this is a 1D form of equation 19. So we now have two tools in our toolkit. The first is that the area under a Dirac delta is 1. The second, when you're ready, the second is that the Dirac delta sifts. If I was to say this in plain English, it would be the following. Any integral involving the Dirac delta is trivial. Here's an integral which has a Dirac delta inside it. Any integral that has a Dirac delta inside it is trivial. Because you throw away the integral sign, you don't need to integrate. Throw away the Dirac delta, and what are you left with? F of something. There's f of something. What do you put in the argument? Well, you force this to be naught. X minus x naught equals naught. X equals x naught. X equals x naught. So just to repeat, in English, this sifting property of the Dirac delta, equation 19, says that any integral involving the Dirac delta is trivial. Here's an integral involving the Dirac delta. You throw away the integral. You throw away the Dirac delta. You throw away the whatever. What are you left with? F of something. F of something. What is that something? We'll set the argument of the Dirac delta to naught. X equals x naught. X equals x naught. So this is a second of 3 tools that we'll need. By the way, there's only 5 tools in all of Fourier analysis. There's 2 that we never use, so there's only 3 that you need for this course. We've just done 2 of them. What's the third one? The third one is equation 17. I've been banging on about this idea that you can express any function as a sum of plane waves. Now, the Dirac delta is not a function. It's something more perverse, more bizarre, more singular, more badly behaved than a function. But even so, this can be expressed as a sum of plane waves. So let me give you the same logic that we gave when making arbitrary wave functions out of plane waves. And since we're in 1D, this is a one-dimensional plane wave. Let t equal naught. E to the I kxx, yeah? Kx is the x component of the wave vector k. If we had a 3D plane wave, just to be explicit, it's this. If we freeze time to naught, this goes. This is going to have Cartesian components kx, ky and kz. This is x, y and z. This dot product will hence be kxx plus kyy plus kzz. But here we're living in a one-dimensional world, so we just have this in the exponent. So this is one plane wave. I'm going to need to multiply by some coefficient, which is infinitesimal, and then add them all up. And that should let me make an arbitrary function. This is not a function, but it's a very, very bizarre object. We can still express it as a sum of plane waves. And the coefficients are all 1. Or more precisely, the coefficients are all 1 on 2 pi. So 1 on 2 pi. So this is how you make a Dirac delta out of plane waves. If I was to give this a fancy name, I'm not going to write it out. This is a Fourier integral when you're adding up plane waves. That's a Fourier integral. This is the Fourier integral representation of the Dirac delta. Just to repeat, this is the Fourier integral representation of the Dirac delta, and this is equation 19, or its 1D form. But I told you, never believe anything I say, never take anything that I say on faith, ever, without being able to prove it to yourself. You see also that I often take pictures which are good because they're conceptual and therefore directly understandable, but you need to take the next step, which is to take those concepts and mathematise them precisely. You could just work in a purely mathematical sphere and you would miss out on that conceptualisation. You could work in a purely conceptual sphere and miss out on the precision of mathematics. Again, I argue that you need both to have a proper understanding. So with that in mind, let's look at this from a conceptual perspective, and then I'm going to leave it to you to look at it from a mathematical perspective. And I'm about to have a mental blank and ask you a question. All right. So the claim is that this is the integral representation of the Dirac delta. Whenever I don't put limits on my integrals, I mean that the limits are infinite. So whenever I don't put limits, I mean infinite limits. What's a way that I can simplify this integral? Multiply by 2. And change the limits from 0 to infinity. Now the reason we can do that, this is good. This bit's good. I don't like this bit. What don't I like about this? Let me give you a clue. The idea is a very good one. We're going to push it through. Let me write this as cos of kxx plus I sine of kxx. So this is now two integrals. Any words pop into your head as you stare at this? Sorry? It has an imaginary component. So there's a real part and there's an imaginary part. All right, so this is our Dirac delta. There's a real part, which is 1 on 2 pi times the integral of cos. And then there's an imaginary part. And I'm actually losing interest as I write, right? This imaginary part, I don't ever want to write it down. Why not? Why don't I want to write down the integral from minus infinity to infinity of sine kx dkx? Beautiful. This is an odd function. And because we're integrating from minus infinity to infinity, the integral of that odd function, in fact the imaginary part of this integral, as you're mentioning, disappears because sine is odd. And now can I return to that idea of the 2 and the 0? If we multiply this integral by 2, because this is even, we can multiply the integral by 2 and replace the lower limit with 0. Now I've lost interest in the mathematics, and because I need a picture, haven't drawn a picture for too long. I'm going to ask a deliberately vague question, which is the following. Describe this equation in one sentence of plain English. So there's my question. Describe this equation in one sentence of plain English. Who'd like to have a shot? Cool. Let me just make an aside. When I'm doing research, which is about half my time, or about 40% of my time, let this be the stuff, all the stuff that I know. When you're doing research, you're working on problems that no one knows the answers to. You're working on problems like why, which lie outside what you know. Therefore, you're confused. Therefore, you don't know what the hell is going on. Therefore, you don't know the answer. Therefore, you make a lot of wrong statements. It's no exaggeration to say that when I'm doing research, I'll be wrong 95% of my time. The point is, it's okay to make mistakes. I make them regularly, several hundred a week. No exaggeration when I'm doing research. So if I throw out a question, feel free to belt out an answer. If it's wrong, that's cool. That's one of the ways we learn. Now, if I was to be asked to describe this in words, I would say add up every cos graph. I'm just conceptualizing this. Add up every cos graph. For every possible value of kx, you'll have a cos graph. Cos of 1x, cos of 2x, cos of 1.6x, cos of pi x. Every single possible real positive, non-negative value for kx gives a cos graph. And this just says add up every cos graph. Okay, it's a function of kx, but that's by the by. So here's one cos graph. I just want to pictorialise this. And here's another cos graph. And here's another cos graph. Notice that they always go through 0, 1. But everywhere else we have a mess. This is conceptualisation of this. Add up every cos graph, and you're going to get infinity when kx equals 0. But out here, it wouldn't be surprising if there was some sort of massive cancellation. Fair enough. This gives a plausibility argument for why adding up every single cos graph might give something which has a blip of infinitely skinny, infinitely high blip at the origin. But that's unsatisfactory. That's a picture, that's a hand-waving argument. How do we render this more precise? It's the following. And the key is this idea of limits of functions. I look at this integral representation of the Dirac delta, and instead of having infinite limits, let me have finite limits. So I've just taken nothing more than written the definition of the Dirac delta, which I'm trying to prove, and just saying, let's have finite limits, which we're going to take to infinity. This integral is elementary. You can do it. We want to render precise what I've described here. We want to show that the equation at the top of the board is in fact the Dirac delta. This integral is elementary, so do it. And when you do it, what you'll get, if m is non-zero, what you'll get will be something like this. It'll be a blip, and that blip will have a width that's proportional to m, and it'll have an area of 1. If you make it'll have a width of 1 on m. And as m becomes infinite, this will become an infinitely skinny, infinitely high blip with area 1, which is precisely the Dirac delta. I invite you to actually work out this integral, write it down, graph it to prove these statements. So we have 3 elements of our toolkit, equations 17, 18 and 19, which I've written in one-dimensional form. These are the only 3 tricks, just to re-emphasise, that we use for the entirety of the course, but we use them relentlessly, which is why we're having this tutorial. What I want to do now is to write down the 3D forms of these equations. So let's begin with 17, the equation we've just proved. So when we're in 1D, and I'm going to rub out this x in a moment, when we're in 1D, our equation looks like this. If we're going to go to 3D, this is now a Dirac delta. Instead of a function of position x in 1 dimension, it's a function of position r in 3 dimensions. This 1 on 2 pi becomes cubed. The single integral becomes a triple integral. Kxx becomes the wave vector k, dotted with r, and dk becomes dk. This just says add up every plane wave at t equals 0, add up every plane wave, and you'll get a Dirac delta. That's the 3-dimensional version of the picture I've given earlier. How about the idea that the area under the Dirac delta is 1? 1 equals the area, now in a 3D sense, under the Dirac delta. The Dirac delta is now 0 everywhere in 3D space except at a point, but the integral of this object over all space is 1. And the third and final element of the toolkit is the sifting property of the Dirac delta. Any integral involving the Dirac delta is trivial. Throw away the integral, throw away the Dirac delta, throw away the whatever. What are you left with? F of something. What is that something? Set this to 0. R equals R0. R equals R0. So these are the 3-dimensional versions that we need for our course. Again, everything you need to know about Fourier analysis is here. When you're doing proofs in quantum mechanics that involve Fourier analysis, there's only 3 tricks. If you're stuck, try something. Another point, One of you was mentioning, a few of you were mentioning these exercises are really hard. They are. That's why I've given you solutions. Unlike previous years, every single exercise is unique. Every single exercise is different. Every single exercise needs some tricks. The first time you see me use a trick, it's a bizarre alien concept. But the fifth time you see me use a trick, you'll say this is a familiar tool. These are the tools in the toolbox. If you get stuck, just use one of the tools. It'll either work or it doesn't. If it does work, you can continue. If it doesn't, try a different one. Hugely important problem-solving technique. Ask yourself, what can you do? Even if it's a crazy quantum problem with six-fold integral, there's often only 2 or 3 things you can do. Just try them if you don't know. Trial and error. Again, none of the problems in quantum physics, I mean, this is quantum physics after all, none of the problems are routine. But once you start seeing through practice and hard work and sweat, you'll start to see patterns. I just use the same tool again and again and again. But it's only through hard work and practice that you can get there. All right. This is the toolkit. Now, I've just spent 25 minutes rabbiting on without actually solving the question that we want to solve in exercise 9. What is the question? Remember that we, in this morning's lecture, expressed an arbitrary wave function as a sum of plane waves. Here's a plane wave. Here's a weighting function that's infinitesimal. Weighting function that's infinitesimal. Here's adding them all up. And 1 over 2 pi cubed is a pointless convention constant. There just because of historical convention, 1 over 2 pi to the 3 on 2. Again, I emphasise this was a Fourier integral. You give me the momentum space wave function, I'll synthesise, I'll use those as weighting coefficients to add up the plane waves to give me an arbitrary function. So this tells you, this equation, equation 15, tells you how to go from the momentum space wave function, which is one way of representing the quantum system, to the wave function. That's 15. We want to prove equation 16, which is how to go in the opposite direction. Equation 16 is how to go in the opposite direction. And this will be an example, a challenging example of the Fourier toolkit in action in a quantum setting. All right, I'm going to begin by just writing out equation 15, but I'm going to leave what I call judicious gaps. So the wave function is equal to our pointless constant, or our convention constant, times the triple integral, again note the gap, our weighting coefficient, our plane wave, k dot r minus omega t, decay. Now we need to be very careful here. So there's no prime yet. There's no prime yet here. That k that appears there doesn't really exist. This is a dummy variable that's integrated over. So this object here is certainly not a function of k, because that's been integrated over. So this k and this k and this k are integrated over, and that's reflected in the fact that there's no k on the left-hand side. The point here is that k is a dummy variable. That doesn't exist. So I could call it whatever I want. I could call it the vector k, I could call it the vector w, I could call it the vector Albert Einstein. I could put a smiley face there, it would make no difference. As long as those 3 k's have the same symbol, it can be whatever I want. Now I'm going to need a symbol k in what I'm about to do. So to differentiate this dummy variable k, you know, I can't just shove a k out here. Suppose I wanted to multiply left and right hand side by k. So I put the right hand side, I put a k, and the left hand side, I put a k. That's wrong. If these primes weren't there, then this k is a fair income k. This is a free variable. These k's are dummy variables. I need to distinguish between them. So since I'm going to stick some k's outside this integral, I need to put primes on these k's. The next thing, I want to prove equation 16. So I'll look at the answer and I'll work backwards. Classic technique, right? Look at the answer and work backwards. Nothing wrong with it, we do it all the time. I look at the right-hand side of equation 16, and that's a nasty integral which has this at its heart, right? The right-hand side of what I want to prove, the right-hand side of equation 16, has this at its heart. So let's just take this equation and make the left-hand side of this look like the right-hand side of 16. Just to repeat, I want to make the left-hand side of this look like the right-hand side of 16. What is the right-hand side of 16? Well, it's 1 on 2 pi to the 3 on 2. I'm just writing down what I want, yep. Triple integral of psi of RT, e to the minus. This is actually what we want to prove, right? So on the left-hand side, I've shoved this red chalk there, and it makes the left-hand side of this equation look like the right-hand side of what I want to prove. So I need to show that this equals psi tilde of k. This, by the way, is called a tilde. And now you see why I put the primes here. Because this k is a free variable, this one is a dummy variable. And what I do to the left, I do to the right. So I multiply by 1 on 2 pi to the 3 on 2. That'll make this cubed. I stuck a triple integral there. I multiply by e to the minus, k dot r, etc. And then I have a dr. Fair enough. So this is the left-hand side, so the right-hand side of 16. So the first expression is the right-hand side of 16. And that equals this horrible expression at the bottom of the first panel. Now at this point you're thinking, what the hell do I do with this? It's got 6 integrals in it, and it's got an arbitrary function psi tilde. That looks really hard. It's not, and it's not hard because psi is arbitrary. If I say to you, integrate an arbitrary function, the answer is very simple. You can't, right? That makes your life easy. You can't integrate arbitrary functions. So all that mad stuff about integration that you learned is all good, about integrating particular functions, but it's useless here. Arbitrary functions are easy to integrate because you can't integrate them, therefore don't even bother trying. There's very little you can do. So you look at this hard expression and you ask yourself, what do I do? And the answer that I would always fire back is, what can you do? List what you can do. One of the very few things that we could do here is let's just simplify by siphoning all the integrals out the front. We've got 1 on 2 pi cubed. We've got 6 integrals. Okay, it's not as scary as it looks, but a 6-fold integral. And then I'm just going to write out everything we have. We have our momentum space wave function. We have a product of 2 plane waves, and I want to siphon off the position dependence into one expression. And the time dependence into another expression. And then I have decay prime and dr. Again, that looks mad, but there's almost nothing we can do, and that makes life easy. So the question is, what can you do? Can we apply one of the elements of the Fourier toolkit? Not obviously. One of the very few things we can do, one of the only things we can do, is to interchange the order of integration. Very commonly used trick. If in doubt, give that a shot. Sometimes it'll work, sometimes it won't. If it doesn't, try something else. That's trial and error. So what I want to do is to interchange the order of integration. Now, I'm slightly dyslexic, which is very bad for a theoretical physicist. So I need to do some accounting here. What do I mean by that? Well, I want to have dr as the inner integral and decay as the outer integral. Yep, so dr and decay. So my outer integral is over k, and again, to make my life easy, I'm going to put brackets here. Yep, so everything in the square brackets is going to be integrated over k, and dr is manifestly the inner integral. Everything that goes in angular brackets is going to be integrated with respect to r. So what's in angular brackets? Anything that depends on r goes in here. Anything that doesn't depend on r goes here. So this is what I mean by accounting. What do we put where? So there's two slots that we can put this into. Do we put it into slot 1 or slot 2, and why? Go for it. Yep. Beautiful. This object here does not depend on r, therefore we're not going to put it here, we're going to put it in slot 1. Thank you. The next thing, this does depend on r, so we're going to put it in here. E to the I, k minus k prime, dotted with r. This object here does not depend on r, and therefore it goes in here. So we've done one of the very few things that we can do, which is to interchange the order of integration. Can you still hear me? Thank you. At points like this, you say, what can you do? Well, we've interchanged the order of integration. We certainly can't do an integral with an arbitrary function, so forget about this. Let's look in here. And then you ask yourself, can I use an element of my toolkit? So if I, as a hint, underline this as a place to look, because I certainly can't integrate an arbitrary function, let's focus on the inner integral. Which element of the toolkit would you use and why? Why would you not use the sifting property of the Dirac delta? Beautiful. There's no Dirac delta here, right? Sifting property of the Dirac delta, you need a delta. There's no delta here. So we're not going to use this one. For the same reason we wouldn't use 18. I mean, this is the kind of logic that you need to do when solving problems. You need to be, whether you're doing quantum mechanics or whether you're doing management consulting, you need to cut through the bullshit and to say, what is the simplicity here? You need to think with brutally clear logic. There's only 3 things you can do. Try them. But 2 of them have got deltas in them. There's no deltas there, therefore you must use 17. That kind of logic, on the one hand, is you know, this is hard quantum physics. On the other hand, it's a process of logical deduction. Try and stand back from the problem and use that level of logic. This is the only thing that has no Dirac delta, and there's definitely none there. I was talking about k as a dummy variable before. So let me vandalize this equation. K is a dummy variable. I can call it whatever I want. I could call it the face of Albert Einstein. I could call it a filled-in circle. So just to emphasise the fact that that's a dummy variable, it's integrated over, it doesn't exist, let me call it a filled-in brown square. Okay, you'll never see that in the textbook, but I've just done it. Similarly, this is a free variable. This can be anything. Whatever it is, it could be a square, it could be the vector r, it could be the vector r times a hyperbolic tan of the sine of 62,000 theta cubed. Whatever it is, I'm calling it square, and whatever it is, you shove it in here. The 2 pi cubed, let's bring it over to the left-hand side. And let's now look at this template and look at this object here. Yep. If you integrate e to the circle dot square decircle, you get delta as a function of square. Just to repeat, okay, these things have to be vectors, but with that understanding, if you integrate e to the I, circle dot square, decircle, the circles are gone, you're left with a function of square, which is the Dirac delta up to this multiplicative constant. Same thing here. R is integrated over, R is the circle. I can call it whatever I want, let me call it circle. What am I left with? I'm left with, up to a factor of 2 pi cubed, I'm left with the Dirac delta. What do I shove as the argument of the Dirac delta? It's whatever I didn't integrate over. It's whatever I didn't integrate over. It's whatever I didn't integrate over. So we've just used this element of the toolkit. So let me put a tick here. The fact that I've used that tool probably means I won't need to use it again. Not always, but often. So maybe these are the next two tools I need to look at. All right, what am I left with? Now remember, this is the right-hand side of equation 16. We want this to reduce to the left-hand side of 16, which is psi tilde of k. So we want this six-fold integral to reduce to psi tilde of k. In other words, we want to get rid of the integrals. In fact, both of these get rid of integrals, right? 3 integrals are gone, 3 integrals are gone. So that logic doesn't help. But again, trying to stand back and think in plain English. Let's just write out what we've got. 1 on 2 pi cubed, cancellation. You should always feel good when things cancel. Triple integral. 3 of the integrals are gone, that's good. Psi tilde of k. E to the I. Omega minus omega prime t. By the way, there was something I forgot to mention earlier. This omega was also primed because k was primed, and because omega is a function of k, this omega was primed. Just to repeat, because I primed the k's, and because omega is a function of k, and then the omega also needed to be primed. All right, so we have triple integral, psi tilde of k prime. We have this thing, and what's underlined is a Dirac delta and decay. That's good. Again, that looks like a really hard integral, but you can't do the integral in general because, sorry, you can't integrate as in methods of integration because this is arbitrary. So we can't think about how to directly integrate this. What tool do I use now to proceed, and why? Um, 19. Beautiful. So this is correct. We can use 19 because this will sift. Any integral involving the Dirac delta is trivial. Throw away the integral, throw away the Dirac delta. What are you left with? F of something. What is that something? Set this to naught. R minus R naught is naught. R equals R naught. Exactly the same logic here. Now this looks less complicated than this. But notice I said any integral. Yep, any integral. This has an f of r. This has something different. This is integrated over r. This is integrated over k. That's fine. Think of that plain English statement that I just made and let it guide us. This is an integral involving the Dirac delta. So let's think through the words. Any integral involving the Dirac delta is trivial. Throw away the integral sign. Throw away the Dirac delta. Throw away the d whatever. What are you left with? Sorry, that 2 pi cubed shouldn't be there. We're left with this shell of a function. We need to set this to naught. In other words, k has to equal k prime. If k equals k prime, then omega will equal omega prime, so that's gone. And if k equals k prime, then k prime equals k. Yep. But this is the left-hand side of 16, which makes us happy. By the way, when I was taught mathematics, so I very stupidly, when I was taught mathematics many years ago, when a proof was completed, I was expecting to see QED, but my lecturer wrote down BYU, and he said that he'd actually submitted a paper which had every proof ending with the word BYU. They were told to change it. Instead of QED, BYU means Bob's your uncle, but it's a way of saying QED. You're allowed to put that in your assignments and in your exams at the end of proofs. But the point is we've now proven equation 16. And the key thing here again is synthesis versus decomposition. Equation 15 lets us synthesize arbitrary wave functions as sums of plane waves. Equation 16 does the opposite. These are Fourier integrals. They're spoken of as a Fourier transform pair. I want to return to one small point that I mentioned. It's an important one. I mentioned that angular frequency is a function of k, k being the wave vector, so the magnitude of the wave vector. Where do I get that from? Velocity equals frequency, nu, times wavelength. Instead of putting the wavelength in the numerator, I can have 1 on the wavelength in the denominator. I can multiply numerator and denominator by pi, and I'll get that the velocity equals 2 pi times the frequency, which is the angular frequency, divided by 2 pi on lambda, which is k. Hence omega equals vk, which proves that omega is a function of k. That's it. Thank you. And as always, happy to answer questions after class for as long as you want. Thank you.